Hello everyone. In this talk, I will speak about Gaussian mechanism design for prescribed privacy sets in data releasing systems. My name is Teymur Hossein Alizadeh, and this is a joint work with Nima Munshizadeh. Both of us are from University of Groningen, the Netherlands. First, I introduce the topic and motivate my problem. Then I formally define the problem. Then I talk about Gaussian mechanism design and how can we do it in an optimal way. After that, I present a case study. Probably you are aware that Elon Musk bought Twitter for about $44 billion. Well, he could have many motivations, like making more money or having his own media. Here I argue that maybe privacy actually was one of the reasons. The thing is, Elon Musk has a private jet, and this private jet needs to send the location to flight control towers. But there was this teenager who broke the communication line between Elon Musk's jet and the flight control towers and published the online location on Twitter. So here you can see that he is saying that Elon Musk took off from Austin and probably he goes to Los Angeles, and 2 hours later he says that, okay, he landed in Los Angeles. So if this played 1% role in the reasons that why Elon Musk bought Twitter, then privacy actually cost about $450 million. To be clear, Musk suspended the Twitter account after he bought Twitter. Okay, so let's solve this problem, at least on paper. So for the problem formulation, consider a linear time invariant system here with x and u and y is in the given dimension and m and p. Here I say that we have this system, linear system, which releases the data, input and output, and send it to another party for many reasons like monitoring, safety, security, or even for designing controller, data-driven control, which is a hot topic right now. And my assumption is that xk, the state trajectory, actually include privacy-sensitive information. To make it more formal, I assume that everything except x0 is publicly known. So if you are an adversary, you already know the output, you already know the input, A, B, C, D, and any kind of privacy mechanism that I will use later on. And also the system is observable. So here I propose a candidate solution. Suppose that you add noise to the initial condition, and I here use Gaussian noise with covariance sigma b and 0. Then if you essentially let the system to have the initial condition x tilde, then an adversary, which here is maximum likelihood estimator, can estimate x0. They get x0 hat, but for that x0 hat, they have a confusion set, which is a covariance of their estimation. And this covariance is exactly sigma b, the amount of noise that you added in the first place. This was an easy solution, so essentially we solved the problem. And the second thing that I really like about this solution is that it gives us a prescribed confusion set, which is given by sigma b. And in order to see that, you should recall the confidence ellipsoid. Here is Q, which is entirely characterized by sigma b. So the estimator estimates x0 hat and says that x0 is in this ellipsoid. This is the amount that he or she is confused about the true x0. And it is entirely characterized by sigma b. So by shaping sigma b, and by choosing different value for sigma b, you are essentially shaping the confusion set that the adversary faces. And hence the name of my paper, which says prescribed confusion sets. So, but this solution actually is not feasible, as you can see, because maybe you cannot change the initial condition. But it's not even desired, because if you have a chemical reactor, essentially you are saying that change the initial condition of chemical products and then let the chemical reactor to perform its task. And this doesn't, this is not what you really want. So another idea would be, what if we add noise to the output of the system? Here I say, this is Y, which include all the output, concatenated output. And if you add noise nk minus 1 to it, using this noise, which has a covariance sigma, capital sigma, then the estimator can actually, the adversary can estimate the initial condition state because they have everything. They know the covariance, they know the output, And here in this case, what they get as the covariance of their estimation is not just the noise, but also the dynamic of the system. So a good question arises here is that I like the first solution, which was shaping the confusion, but it was not feasible. So the problem would be, can I get any confusion set using the output noise? More formally, can I pick a covariance for the Gaussian mechanism for the output case such that the covariance of the estimator would be anything predefined by the system designer? So if I set sigma b, can I design sigma, a positive definite matrix, such that I get this confusion set? Well, here in the theorem, actually, I answer this question. In the first part, I say, okay, let X be the set of all matrices that satisfies this equation, then this matrix equality. And this set, let's call it S of X, is not, the first statement actually said, is not empty. So you always have a matrix X such that satisfies this equation. And this set is defined using this relation, which M and N are basically, they depend on OK and observability matrix and observability gradient and also the noise. Okay, but in the second case, I say the set of positive matrices actually is not empty. So you always have an X such that this X is positive definite and satisfies this equation. And this is a good news for us because we always can have a positive matrix as a covariance of the Gaussian noise. And the third result says that your set, the Sx positive, is a singleton when the pk is equal to n, which means the number of the state is equal to number of the output times the time steps. Okay, so this is a good news because we always have a solution for the matrix equalities that we have. So in the next step, we try to use this degree of freedom and pick the best covariance that give our desired performance, which I define later. So if we want to add noise to the output, intuitively, we don't want to ruin the output. And for not doing so, we say that the difference between the perturbed output and the clean output, let's call it Z of K as the error, and the expectation of the energy of it can be shown that it is related to the trace of the nodes, the trace of the covariance. So again, intuitively, we say that I want the confusion set, but I want to do it with as little noise as possible. That's why I here minimize epsilon, which is the trace of X inverse, which is an operand on the trace of X inverse. But this is not a complex problem, and it doesn't have a global solution in this one, at least. Or it's a global solution cannot be found easily. And you can see why this is not convex. Essentially, the R, which appears in X as well, you have both R and R inverse. So I try to convexify the problem, and I use a simple trick by upper bounding trace of X inverse using trace of X inverse is lower than pk over lambda min of X. And I replace the constraint with this matrix inequality. So, and I define beta to be pk over epsilon. So instead of the original non-convex problem, I propose this problem, which is maximizing beta, which means minimizing epsilon, subject to this linear matrix inequality. Here, R and beta are by value. And this, so this problem can be solved using CVX or any other favorite softwares that you have in mind. But I do so in the case study, but actually I show you later in the next theorem that we can speak further about the optimal value of this problem. So consider the confusion sets that we wanted to have, which appear in here. And then we did a lot of steps to reach the optimization problem number 9. And this theorem says that the optimal value of the objective function is actually lambda min of sigma inverse times W inverse. So recall again that beta was pk over epsilon. So this theorem essentially says that the best error that you can get, the lowest error that you can get, is equal to pk times lambda max sigma W O. So both observability gradient and covariance plays roles here. No, I didn't put any constraint on the covariance matrix that I wanted to get the sigma. This means that not necessarily that the covariance I get is not uncorrelated, so it is correlated noise. What if we want to have a structured covariant noise? One of them is making sure that each sample actually is independent from the others. So I call it a structured covariance for the noise. And similarly, you can have this program. But this program, in the second constraint, we are essentially want to have the confusion set that we desire using a sigma PLK, which is a structured covariance. And now you have the feeling that this problem actually may not be feasible. And the best that we can do, or one of the methods that we can solve the system, approximate it and make sure that this constraint actually holds within a desired errors that we can define using for example, probability. Okay, as a case study, I consider an HVAC system with this equation. What does this equation say? This equation relates the temperature of each zone to the temperature of the outside and also to the temperature of the airflow that comes to that zone. And here I assume that I have only 4 zones, and I measure the temperature of room number 1 and 4 and send them to a monitoring station. And before doing so, I add noise to them because I am concerned about the privacy. And which rooms I am concerned about? Here I assume that room number 3 and 4 are actually more privacy sensitive. And you may ask that, how is this model and how HVAC system can cause problem about privacy? Well, a simple attack on the system would be to infer presence and absence of people at work using only the measurement of the HVAC system. So here I set the sigma v to be this diagonal matrix, which actually says that room number 3 and 4 are more privacy sensitive compared to room number 1 and 2. And I consider a model where the HVAC system is actually considered at the end of the day. And at that moment, the input of the system, which is m.set and q.offset, they are off. So essentially, we have this linear system with the parameter m and r. They are picked uniformly randomly. So here, by having the temperature, then this adversary can find out that who was at the office or who wasn't. So in order to compare my method with another method, which is differential entropy, another idea is to put a measure on the confusion set, here differential entropy log determinant, and within an error budget, try to maximize that measure. So this is the case study that this is a method that I will compare my method with. So as I said sigma b to be decimal. I solved the optimization problem and I received sigma. And by getting this sigma, we also had epsilon optimal. And I put the epsilon optimal here as the budget of this optimization, and I get the sigma d of the other bit. And if you do so, this figure shows the confusion set. The blue one is the sigma b that we desire. And as it says that the confusion set along the temperature of the room number 4 is way bigger than the temperature of the room number 1. But this is not the case for the differential entropy. Differential entropy essentially maximizes the volume of the ellipsoid, and it doesn't care about each axis. And this also shows the temperature of temperature, which is the blue one, and also the noisy measurements that I send to the monitoring station. So in this talk, I hope that you are convinced that privacy is actually important. And my main message is that any confusion set by correlated knows that the output can be achieved for the 4x0, which gives the system designer more degree of freedom. And as a future study, we can work on the privacy of the input, and also we can integrate the method with controller design. Thank you very much, and I see you in the offline meeting as well.